Very good afternoon. We are going to talk about circle diagram. So just we have seen what we mean by the circle diagram. It is nothing but a graphical representation of induction motor's equivalent circuit. It means whatever information you can obtain through equivalent circuit, the same information can be obtained using circle diagram. Circle diagram has certain advantages because of its simplicity and the quick estimation of the induction motor operating characteristic. So that can be easily obtained. Induction motor characteristic parameters that can be obtained using circle diagram. That's why this is considered as advantageous, and also it is popular because it gives you accurate result for practical purpose, though it is based on certain assumption. It also gives you panoramic view. So we started with circle diagram with understanding the locus of the current. So what we have done, we have just for understanding we have considered the rotor equivalent circuit, and then we have determined the expression for its EMF. Then this EMF is rewritten in this form, which is basically indicating that it is a current, and this current has two components. So how we have obtained the rotor locus for the rotor circuit, that just we have taken E2 as a reference. From E2 we have drawn I2, which is given by OA, and it will be lagging by theta 2 degree from E2. So now what you are having this I2 is with U. The first term, the minus j E2 by x2, it is a current which is lagging E2 by 90 degrees. So that is drawn here. Minus j E2 x2, it will be making an angle of 90 degree. And this component which is given by minus j I2 R2 by S x2, the current component, basically it is lagging I2 by 90 degree. So I2 is here. From this I2 you can draw this current by at 90 degree you can draw this current. So basically here what you could see, this is giving your OA, that is giving you I2, and now if you could see that this is nothing but rectangle. So whatever is this I2, if this is the I2, so this will be also I2. It means the CB, that is also indicating I2 here. The OB, already we said it is minus j E2 by x2. Here your AB, that will be equal to this AB, that will be equal to OC. So OC is known to us. So this, the value of AB, that will be given by this value similarly. Okay, so because it is a rectangle, so the value would be the same. Then what you could do, you can okay, just I have shown this for better understanding. So this part already we have seen. Okay, then basically you could see that the angle OAB, we are talking about this angle OAB, it is a right angle triangle. So this point A, it must lie on circle when you are drawing a circle and taking diameter as OB. So just take diameter of OB, or you can take the half of this value as a radius and draw a circle. So this point is going to come, the point A, that will lie on the circuit. It means the rotor current that is lying on a circle. So basically what it is indicating or implying or showing here, that the locus of the tip of rotor current phasor is a circle. Diameter we have seen, so it is a circle. So because rotor has tip on the circle, so stator current, it must lie on a circle. So this is basically basis of circle diagram, why we are calling it as a circle diagram. Okay, that rotor current, it is coming, the tip of rotor current you could say, that lies on the circle. So it becomes your circle diagram. So anyway, this circle is shown here to indicate that the rotor current tip is lying on the circle. So I have shown you the circle. Already it was drawn, just I have shown later on for clarity. Then let us determine the circle diagram from the approximate equivalent circuit. So we are having this approximate equivalent circuit. What we have noticed here that the shunt branch element, it consists of, we are considering here shunt branch element, but see its position. Where is its position? So when you are considering it before the resistance, leakage resistance and leakage reactance, it means the drop due to this exciting current is neglected. So that is assumption in our case. Where we are considering the location of the shunt element, it is before leakage resistance and leakage reactance. So what would happen? The IE which is supplied, that will directly go here. Okay. Otherwise, the IE, if it is flowing through this leakage resistance of stator and reactance of rotor, so the drop will be added there due to this current. So here it is the assumption. Then what we will do, we are going to take apply KVL and find out the V1 in the outer loop. So you are going to get this expression where theta 2, that will be given by tan inverse x1 plus x2 divided by r1 plus r2 by s. Already we have seen the basis of the circle diagram. So what we are going to do, from this expression we are going to determine the current. So how that can be determined? Just you need to divide both sides by x1 plus x2. So this term, the first term, that will become minus j v1 upon x1 plus x2. Basically you are dividing by j x1 plus x2. So here again j is multiplied in denominator and numerator. So in denominator you will be having j square. J square is nothing but it is minus 1. That's why this will become minus j. Okay, so minus j v1 divided by x1 plus x2, it is nothing but a current, okay, which is lagging the v1 by 90 degree. This consists of two components, that is the rotor current, it consists of I2, and the another component of current which is lagging I2 by 90 degree. Okay, so you are having this circle diagram. You have to take V1 as the reference. So V1 will be your reference. From V1 at an angle of theta 2, you will be having I2. Before that, what you can draw? You can draw this current component if you want. Otherwise, after that you can draw. So this current, that will be lagging V1 by 90 degree. So V1 is taken as a reference, and then after from here 90 degree you can draw the V1 divided by x1 plus x2. Okay, so basically you are having this component, and once I2 is drawn, from I2 at 90 degree you can draw this component of current. So it is lagging by 90 degree. And similarly what we have seen, the tip of the rotor current, if you draw a circle having the diameter of this one, V1 divided by x1 plus x2. So take this diameter, or half of this will be radius, and this will be your origin. So when you are going to draw a circle, what would happen? The tip of the rotor current, that would lie on circle. So that we have discussed, and for approximate equivalent circuit we have drawn this circle diagram. So here OA, it is representing your rotor current. This will be your AB, similar to previous case, the OC, parallel to OC we have drawn one line AB here. So this AB and OC, that will show you this component of the current, I2 into R1 plus R2 by S divided by X1 plus X2. At standstill condition, what would happen? When the applied voltage is here V1, your current I2, that will be very large, and your theta 2, it will be also increasing. So its value would be given by this one. Here I2, that will be given by basically this OD. I2, that will be given by OD. Then in previous case, whatever we have observed, that was observed for the outer circuit. Okay, just we have applied to outer circuit. It means shunt element, that is magnetizing reactance, and the core loss component is not included in previous case. Now we are going to include that. So how it can be included? You have taken V1 as a reference, and this one is your you can say a horizontal axis. So what you need to do, you have to show the magnetizing current. Magnetizing current can be shown this from O to Q dash. This is your magnetizing current, and the core loss component that will be usually in phase with V1. So you can you can show it here. So this Q dash and Q, it is going to give you core loss component. Okay, so core loss component is your Q dash, OQ, it is magnetizing current. So now you know that it's phasor sum in phasor diagram, that is giving you exciting current. So here OQ, that is going to give you exciting current. So what we have seen, your QA, from here QA, then you can proceed with the same circle. You can draw the circle with the diameter. Okay, so your this point basically QA, that is going to give you the rotor current. The QA is going to give you rotor current, and when you are going to take this value OA, basically it is going to give you stator current. So stator current, that includes, that is going to supply basically your exciting current as well. That's why this will be your stator current, this will be your rotor current, and the angle between V1 and I1, that will be your power factor angle on stator side, cos theta 1. And the losses that will be given by when you are multiplying this QQ dash multiplied with voltage. It means what is the QQ dash? That is nothing but core loss component current. IC multiplied by V1, that will give you core loss. So this is your circle diagram including shunt branch element, that is your core loss component and magnetizing current. So core loss component of current, that is included, and magnetizing current is also included. The angle between this reference and this I2, that is going to give you theta 2. It is going to give you theta 2. That is, theta 2 is nothing but it is cos theta 2, that will be your power factor on rotor side. Core loss, friction and windage loss at no load operation, it can be included by considering the length. See, in this diagram what we have done, just notation has been changed. Instead of Q dash Q, just P is there. The remaining thing is same and few more things are added in this circle diagram. So when you are including the core loss, friction and windage loss at no load operation of induction motor, so what you need to do, you need to make this QP length, that should be equal to this no load induction motor loss per phase divided by per phase V1. Means while drawing this value, it should reflect this ratio of no load induction motor loss per phase divided by per phase voltage. So this diagram is little bit zoomed here for our better understanding. Few things we have already observed. So in this circle diagram, what you could see that this QN, this line, hope it is clear to you. It is visible to you. We are talking about this line. Okay, so this QN during no load condition, it will be 0, which is called as I2 dash. It means this point Q is going to indicate no load operating point. No load operating point, that will be given by this Q. And when we know that this QP is nothing but IC. Okay, or you can say it is a constant losses. just we have seen, what we have seen, that core loss, friction and windage loss at no load operation, that will be equal to the QP. So QP is giving this one. So we are having QP, and when you are multiplied with V1, so it is going to give you no load input to stator, and when you multiply the same with V1, that will give you friction and windage loss. Already we have seen. Now this line OP, already we have seen in previous case what it was magnetizing current. So here OP is going to indicate magnetizing current. The no load power factor, that will be given by angle between V1 and this current, that is your IE. So the theta 0, that will be basically this one. You could see this is your theta 0, and it should be equal to no load power input divided by root 3 multiplied by no load current multiplied by V1. Already we have seen the I2 dash, which is equal to Q1, that will be is basically rotor current in no load, its value will be 0, but this is I2 dash, so basically it is referred to stator side. I1, that is this I1O, and which is going to give you the stator current, and the motor operating power factor or stator side power factor, what it will be given by cos theta 1, which is the angle between V1 and I1. So these things, I think it is clear to us. Let us move on. Now this line is drawn. You could see this is a complete circle you are having. There is a point D, and when this line OD, that is basically the short circuit current. It is representing short circuit current when the voltage applied is V1. So you have applied V1 to 3-phase induction motor. At that time, the short circuit current will be given by line OD. D is a point which is also lying on the circle. Please remember this thing. Okay, so under short circuit at rated voltage, the power input, that is going to lost in I square R loss. Where basically it is going to loss, where will be the I square R loss? It will be in conductor. So conductor of what? Stator, rotor, conductor, and as well as it is going to loss the power which is given, that is going to loss in core as well, core of stator and rotor. So stator, rotor, iron loss will be there, I square R losses in the conductor and stator and rotor. So under short circuit condition, whatever you are going to give the input, that is going to be lost. Okay, it is not going to be utilized, but it is whatever energy input you are giving, it will be consumed or dissipated by conductor and iron. So the power input in this condition, that will be basically given by this line DE. Okay, it should be straight. Okay, I could not draw because with free hand. So the DE, it is going to give you power input under short circuit. Basically it is V1 multiplied by this OD cos theta SC. Cos theta SC, the angle between angle during short circuit condition. So theta SC, you could see this is basically your theta SC. OD is a current, short circuit current. V1 is your applied voltage. So angle between this short circuit current and V1 is going to give you theta SC. Here this EF, you could see this EF. Okay, this EF, which will be equal to this QP. EF, that will be equal to QP, because this QP is your basically losses, friction and windage core losses. This line is drawn parallel to this axis. So basically this value would be equal to PQ, that will be equal to EP. So basically this is nothing but it is also indicating your friction, windage and core losses on this side. and this EF, which is equal to QP, that will give you your stator core loss plus friction and windage loss at no load condition, and it will be also equal to stator core loss plus rotor core loss at standstill. There are two different conditions. One is standstill condition, another one is at no load condition. So this is representing EP, that is representing stator core loss plus friction and windage losses during no load condition. When it is standstill, it is going to give you only stator core loss plus rotor core loss. So a slight difference is there. Now this EF, which represents the per phase core loss. So this DF, if EF is representing core loss, please pay attention. EF is representing core loss. So this DF from here to here, that is going to give you per phase I square loss in stator rotor conductors during standstill condition. This is EF, that is basically your stator per phase core loss, you can say. So this value will be your I square R loss in stator rotor conductors at standstill. Now what we will do, we are going to divide this DF in such a way so that this ratio GD to GF, it gives the ratio of rotor I square R loss to stator I square R loss. Rotor I square R loss to stator I square R loss, it is going to give you. So what we have done, just we have divided this DF in such a way so that the ratio of DG to GF is equal to rotor I square R loss divided by stator I square R loss. Then what we will do, now the G is obtained, so you can join Q and G line. Q and G will be joined. So you will get a line QG. Suppose there is an operating point N which is lying somewhere here, okay, at the circle. So draw from here, you can draw a perpendicular to this axis, OX axis. You draw a perpendicular from this operating point N. So basically when you are drawing this this NL, which will be perpendicular to OX, so it will be also perpendicular to this one QR. Both are parallel. Are you getting what we are trying to understand? What we have done, we have considered a operating point N. From N we have drawn a perpendicular to OX. So this perpendicular, this line which is drawn perpendicular to OX axis, and the axis QR which is parallel to OX, so it will be also perpendicular to that. Just trying to give you that understanding. And you can say in alternatively, these axes OX and QR, they are perpendicular to V1. I think there is no doubt. So what exactly we are going to do with this? We are going to determine stator and rotor I square R loss. Basically we are going to show this in circle diagram. Okay, so what we will do, we are going to consider similar triangles. One will be this Q, K and H. This is a smaller one, Q, K, H. And we are going to take another triangle which will be Q, F, D, this bigger one. Two triangles we are going to take here. One is Q, K, H, another one is Q, F, D. So these are similar triangle. So we are going to use property of similar triangle, and we can write this HK divided by DF equal to QK divided by QF. This is nothing but a simple property of similar triangles. So from that we can write this expression. Now what we are going to do, we are going to find the value of QK and QF. So in order to find out this, what we will do, we are going to consider another triangle which will be QKN, this bigger one, QKN. This triangle we are going to take. So from this QKN, what we can write, we are going to determine the value of QK. So QK, it can be written in terms of QN cos angle of NQK. So NQK, it can be, see what we are going to do, whatever is known to us, in that quantity we are going to write the expression. Because whatever is known, that can be utilized, which is not unknown, which is unknown, it must always represent in terms of known value. So what we have done, from this triangle QKN, we have determined the value of QK, which will be substituted here. So we got it in terms of QN is nothing but what it is I2 dash only. So in terms of I2 dash, you are going to get this value. So it will be QN cos angle NQK. Similarly, what we are going to do, the QF, that will be determined by considering a triangle QFD. So from here we can write this QF equal to the QD. QD is your ISC, the known value. Angle will be here DOF. DQF it should be, I think. DQF. It should be DQF, not O. It should be Q. Okay, DQF. So just substitute its value here. Now what we will do, we know the value of QN and QD. Now we are going to determine what you could write the cos angle NQK. So for this we are going to now consider triangle QNR, this angle. So R is basically a point here. What we have done, we have just joined this line N and R. So we will get this angle QNR. Okay, so from this, what we can get the angle cos NQR, the cos, this angle cos N, sorry, cos NQ, Q, this angle we have to determine. So this will be given by QN divided by QR. So here it is QN divided by QR. Similarly, what we can do, now we can join the point D and the R. We can join this D and R, so we will get another triangle, that is QDR. You are having this triangle. From here we are going to determine the value of cos angle DFQ. So we are going to determine the value of DQF, not DFQ, DQF. Basically that we are going to determine. So it will be given by, which will be equal to angle DQR, and it will be given by QD divided by QR. So this is simple, your triangle properties. From that, ultimately we have to determine the value of QK and QF. So substitute its value, you are going to get this HK divided by DF, that will be equal to QN square divided by QD square. So just to substitute what is QN here, QN, it is nothing but your I2 dash, you could see here, and what is the QD? QD is your ISC. So what ultimately you got, HK is equal to I2 dash square divided by ISC square. So this way you can determine the value of HK divided by DF. Now what we will do, we are going to multiply this with and divide by the term R1 plus R2. So ultimately you are going to get this I square R. In terms of I square R, basically you are going to get it. So you are going to get this value. Hope the things are little, it is not complicated. Just you need to find that particular angle. So you need to select particular triangles. So what exactly it is indicating, what we have done, this HK and DF, we got this value. So what exactly it is indicating? It is indicating, if we are saying DF, this, if we are saying this DF is the stator and rotor I square R loss at standstill. When we are saying the current is your QD, if QD is your current, at that time this DF is representing stator and rotor I square R loss at standstill condition. So what we can say? We can say that this HK is going to give you stator and rotor I square R loss when the current is QN, this current. In this case, the current will be this one, QN. So when we are saying the QN is the current, at that time this HK is going to give you from here to here, this HK is going to give you stator and rotor I square R loss. In previous case, if we are saying this is the current, this QD is the current, so the DF is going to give you stator and rotor I square R loss at standstill condition. That we wanted to show you here. That's why whatever mathematics and triangle we have determined, that is shown, just for understanding. Now consider the triangle this Q, K and J. The K is here, J is little bit higher, so very small triangle. Okay, Q, K, J. And we are going to take another triangle, that is Q, F and G, this triangle. Okay, so we are going to take this triangle, and also we are going to take Q, J, H and Q, G, D, this upper one. Okay, so it means what you could say, this KJ from here to here, the KJ that will give you stator I square R loss when your current is QN, and this JH here, that is going to give you rotor I square or R loss at current QN. We are again we are going to consider the triangle, and on the same basis you could come across a conclusion that this KJ from here to here, this much, from K to J, it is going to give you stator I square R loss, and the JH from here to here, that is going to give you stator, JH is going to give you rotor I square R loss, and the current what we are considering here, that will be QN. So you could see that you can represent stator I square R loss, rotor I square R loss, rotor current, magnetizing current, core loss, power factor angle, during short circuit condition current. A number of things could be obtained from circle diagram. That's why we said it gives you panoramic view, and the induction motor operation characteristic can be obtained from the circle diagram at a glance if this is with you. Still many things are remaining. We'll continue. Efficiency and slip. Here what we have seen, this NL, see what exactly NL is going to represent here. It is going to give you total power input. The NL from here to here, it is going to give you total power input. Okay, this KL, it is going to give you basically friction, windage, core losses. The KH, what it was giving you? It was giving you ohmic losses, I square R losses in stator and rotor. So now what you are having? You are having complete losses, you are having complete input, so you are in position to determine the power output or soft power. So what will be your soft power? Our power output, that will be given by basically this input minus losses. So whatever is the loss term, that is still here, KL, that is losses, your KH, it is also losses. So just subtract the losses from the input, that will give you output. So now you can give power output, that will be given by this NH. When you are having output, you are having input, you can find out the efficiency. So what it will be? It will be NH divided by NL. So you are also in position to determine per unit efficiency of induction motor using circle diagram. Now you could, I think, appreciate. Here line QD, this QD, that on which the power output point H lies, it is called as output line. So you can say QD is your output line. Now you start remembering, this is output line. So QD, that will give you output line. In other words, the locus of all power output point such as H lies on the line QD called the output line. You can give the slip. Slip will be given by rotor I square R losses divided by rotor input. So what was the rotor I square R losses? Rotor I square R losses was given by JH. And what was the rotor input? The rotor input, that will be given by the stator input minus losses. So it will be given by JL. JS divided by JL, that will give you slip. So slip can be also calculated from the circle diagram. You can also calculate the torque. What is the torque? Torque is given by your power divided by speed. Air gap power divided by synchronous speed. So you need to find out first air gap power. So NL, that is the total power input to stator, and GL, that is giving you basically stator losses. So when you subtract NL minus JL, means from total input you are subtracting the stator losses, it is going to give you air gap power, the power which is available to rotor, that is air gap power. So from rotor stator input, just subtract the stator losses, so it will give you rotor input or air gap power. So air gap power, that will be given by NL minus JL divided by omega S. So it is going to give you the torque. So here the torque, that will be proportional to basically NJ. This is N, here is the J. Air gap power, it will be proportional to air gap power. Synchronous speed, it is synchronous speed, is it varying or is it constant? It is constant. That's why we are saying it is proportional to air gap power. Here the locus of point J, as the operating point we are considering N, it is going to move the circle. So line QG, this one, the line QG is called as torque line. The line QG is going to represent torque line. Just earlier we have drawn, but we have not shown what we are calling it as. So this line QG is called as torque line. Here starting torque, that will be given by BG. So this value will give you starting torque. We could understand what is the value of a starting torque from a torque for a given motor from circle diagram. Now we are interested to determine what would be the value of maximum output power and maximum torque. So maximum output power, it can be obtained by taking, what you need to do, first you need to find the center of the circle. So this will be your center of the circle C. So what you need to do, you need to draw a perpendicular from the center of circle. Okay, so what we have done, from this center of circle, one perpendicular is drawn, which will be given by CA to the output line. Where is the output line? This is the output line. What we have done, we have drawn a perpendicular to the output line from the center of the circle. So this is CA. You could see that it is tilted one, but it is not tilted one. This is your output line. So what you have done, you have drawn a perpendicular. Perpendicular means what? It should make an angle of 90 degree. So you could see here we have made an angle of 90 degree here. So angle of 90 degree is made. So a perpendicular is drawn. So basically this from here okay, so here what we have done, the maximum output power that is obtained by drawing from the center of circle C a perpendicular CA to the output line QD. So this from here, what we have to do, this AA1 which is drawn normal to this OX is going to give you maximum power output. What you have done, you have drawn a perpendicular and you have to extend it till this circle, and from the circle what you have to do, you have to draw a normal. So this is going to give you maximum power output. Similarly, you can determine the maximum torque. What you need to do, from center of the circle, draw a perpendicular to the torque line and extend it till here, and then you have to draw a normal. So this BB1, that is going to give you maximum torque. So this BB1 is going to give you, so this is your maximum power output line. So it is drawn till output AA1, so A1 point that lies on output. Here the B1 that lies on torque line. So this is your maximum torque, this one is your maximum power output. Here the normal operating region of the motor is near to maximum power factor, which can be obtained by drawing a tangent from this O to the circle. I1 is here starting current, which will correspond to the maximum, this I1, maximum power factor. What we have seen, motoring action. What is remaining? Generating action and braking action. So induction machine can operate as an induction generator. When induction machine is operating as a generator, we will call it as induction generator. So how this operation is obtained? When the speed of rotor is above synchronous speed. So if your motor is running at above synchronous speed, at that time you could say it works as a induction generator. So for this, the locus of stator, that can be given by this one dotted line. See on this side, which is drawn here. This circle with dark line is for motoring. Below that, what you could see, the dotted line, it is for induction generator. So here the power output, that will be given by this ML. Our output we are calling it. Please remember, induction generator. In case of motor, it was input your NL. So power output, it will be given by ML, and this will be your operating power factor. This is V1 here, so V1 axis, and the I, this will be your current. So theta G, it will be the angle between V1 and I. So cos theta G is going to give you the operating power factor. Output current that will be given by basically this IOM. Similar to this, just reverse. Mechanical input from prime mover, how much it will be? It will be given by MH. MH. You need to add the losses. Input, mechanical input we are talking about. So it will be MH. Now braking region, when your induction motor is having a slip greater than 1, at that time we say braking take place. So slip is, you need to make slip greater than 1, so your braking action is going to take place. So you could consider between these 2 points D and S, where S is equal to infinity, you can consider this could be your operating point D dash, which is also going to lie on the circle, remember. So D dash is your operating point where the slip is greater than 1, so braking action will be obtained. Here the torque, the braking torque, that will be given by this dg dash. So what you need to do from this operating point, you have to draw the line in this way. So this is going to give you dg dash, that will be your braking torque. And here the ohmic loss that will be given by, you need to extend this short circuit line. So G dash, that is going to give you basically the ohmic loss. So what you could observe here during braking action, the rotor input, which is D dash G dash, and here the ohmic loss is ZG dash. So when you could see quite easily, this is smaller than this. It means your rotor input that is smaller than rotor ohmic losses during braking action. During braking action. Do you want me to continue or do you want me to stop here? Okay, we will complete this topic in next lecture. Thank you very much.